Morning. We're going to get started on chemical equilibrium. Um, so this is kind of flows right from the rate stuff a little bit, because we started talking in the rate stuff about the fact that certain reactions can happen forward and backwards at the same time. Um, and so this set of notes is a little bit different. You're not going to have everything on your notes that's on here, so I'm going to run through some of this fairly quickly. And I actually have see, I have this pulled up so that I can make sure that I'm kind of hitting everything that's on your notes and not hitting the things that aren't. So we're starting by talking about reversible reactions. Okay. Um, so, uh, Goldberg and Waag or Wog, I'm not sure exactly how you say that, developed the law of mass action, which we're going to talk about in a minute. So they were very instrumental in helping to develop the idea of chemical equilibrium. All right, so, whoops, got to hit the right thing here. Okay, reversible reaction. That's a chemical reaction where the products can react to reform the reactants. Okay, and so basically it's just a reaction where it's happening forward and it's happening backwards at the same time. Okay, it can go in both directions, and we'll show. You'll see plenty of examples of this in the next couple of days. Chemical equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. Okay, so when that happens, then the concentration of products and reactants is going to stay the same. So the reason that we don't notice this happening in more chemical reactions is because, let's say that you have two things in a solution and you mix them together, and then you end up with a reaction. Okay, and let's say maybe your reaction is you end up with a solid at the bottom of your beaker. Okay, so actually let me just draw a picture of this. So you've got your reaction happening. You've got a little bit of solid down at the bottom here. Okay, that formed. Well, at equilibrium, the rate of this solid redissolving is equal to the rate of the dissolved particles that are re-solidifying or recrystallizing. Okay, so you look at this thing, it doesn't look like anything's happening, but on a molecular level, there's a lot happening. It's just happening at the same rate in both directions, so you get no overall change. Okay, so it looks like it's all staying the same. We've talked about that a little bit so far this year. An example of this, mercury oxide, solid mercury oxide. If you heat that, it ends up being in equilibrium, the mercury and the oxygen. Okay, so what happens here is this mercury oxide decomposes, okay, into mercury and oxygen gas, but at the same time, that oxygen gas can re-react with the mercury, and this reaction can happen in this direction as well. Okay, so that's a reversible reaction, and once the rates of those two reactions become equal, then you're at equilibrium. Okay, now just because the rates are equal doesn't mean that the concentrations on each side are equal, which we'll talk about also. Arrows going both directions indicates equilibrium. Okay, and you may see that written like this. Sometimes you're going to see it as half arrows written like this. Okay, every once in a while you might see it like this. They all mean pretty much the same thing. They all mean the same thing. Okay, chemical versus physical equilibrium. So physical equilibrium is a result of an equilibrium between two phases of a substance. There's not a chemical change happening here, it's just a physical change that's going back and forth. And an example of that would be the dissolving example that I just gave you, because that's just a physical change when something dissolves. So once the reaction occurs and you have your precipitate sitting at the bottom of the mixture, then that example of dissolving and undissolving, that's just really a physical change at that point. Okay, so another example of that would be water. So liquid water changing into water vapor, and then the water vapor going back to liquid water. So if it's in equilibrium, then this is happening at the same rate. Okay, which means there's no overall change. Now this is not this is not always the way that it's going to happen. Okay, I mean this reaction is always reversible right here, but it's not always in equilibrium. Okay, because sometimes you leave a puddle of water sitting in a warm area, and the reaction is going to end up, tending to go that way. Okay, and so when that happens, it's not in equilibrium. Now, if you put it in a closed system so that the water vapor can't escape, it's eventually going to recondense, and then you're going to end up with this equilibrium here. Okay. All right. Um, an example of what you would see if you're looking at a concentration versus time graph for something like this. Let's show you this. 2NO2 yields 2NO plus O2. All right. So notice NO2 is your reactant here. Okay, so that concentration is going to be going down over time. And then the concentration of the NO and the O2 are going to start at 0, and they're going to go up over time. Okay, but notice what happens to all of them as we reach equilibrium. They all sort of level out. Okay, and so notice at some point the concentration of the NO is no longer changing, and the concentration of the NO2 and the O2 also are no longer changing. But they are not at the same concentration. Okay, just because you're at equilibrium doesn't mean the concentration of all your reactants and products are going to be the same. It just means the rate of the forward reaction and the reverse reaction is going to be equal. Okay. Another example of a reversible reaction is N2O4 and NO2, and this one's very easy to see as it goes back and forth. You can tell when this one gets to equilibrium because the N2O4 starts out colorless, and so then as some of that changes into the NO2, you're going to start to see this brown gas. Okay, and eventually, once you're seeing no more color change, you've got sort of a light brown mixture at that point. That's when this reaction has reached equilibrium. Okay, so some reactions you can get a very good visual of when equilibrium is reached. So again, concentration versus time graphs here. Just depending on your starting and ending concentrations of these two things, they're going to move in different directions. So if you notice here, initially only the NO2 is present. And I don't think any of this is in your notes. I'm just showing this to you for your benefit here. But in this first scenario, A here, only NO2 is present at the beginning. Okay, so if that's the case, then obviously the NO2 concentration is going to go down as the N2O4 concentration increases. Okay, until you end up with this sort of equilibrium here. Okay. If you start with initially only N2O4 present, okay, and you have none of the NO2, then the reaction is going to go in the opposite direction until it reaches equilibrium. Okay, and then you could start with a mixture of the two present, and then depending on what your mixture is, one of the concentrations is going to go up, one of the concentrations is going to go down. Okay, so again, all this is showing you is you can start a reaction in a bunch of different situations, and here we're varying the concentration, but these reactions are always going to sort of work their way back to equilibrium. Okay, and so that's that's the point of this, is that these things they will move until they get to a constant concentration over time. Okay, now let's talk about the equilibrium constant. This is going to tie in pretty well to what we were just talking about, and this should help us go back and answer one of those AP questions that we were having trouble answering on the last set of AP questions. Okay, so maybe we can go back and hit that in the next day or two. But the equilibrium constant is a capital K, so that's nice and confusing. But it is related to the rate constant. Okay, and we're going to do a lot of different stuff with the equilibrium constant than we didn't do with the rate constant. But the idea here is, if you have a forward reaction A changing into B, like this reaction right here, then the rate law that we would write for that, assuming that this is an elementary step, which we can fairly easily assume that there's just one thing here, right? So the rate law for that would be KF, and F stands for forward, okay, times the concentration of A. KF is the rate constant for the forward reaction. A is the concentration of A. We just said that. If you write the rate law for the reverse reaction, for B going to A instead, then the rate is Kr times concentration of B. And again, the R just stands for reverse. Okay? So let's say we want to find the equilibrium constant here. All right, we're going to do a couple of interesting things. We're going to actually use PV equals nRT on this, okay? And we're going to see how the concentration sort of relates to the pressure on these things. So we've got PV equals nRT, and if we rearrange that, then you can rearrange it to N over V equals P over RT. Now notice N over V here, that's moles over liters. So that's going to equal molarity, okay? And molarity then equals pressure over R times the temperature, okay? So we can substitute for our concentration of A, we can substitute it in the pressure of A over RT. Now you might wonder why we're doing this, but hopefully it'll be clear in a minute. And then the concentration of B, we can substitute in the PB over RT, okay? So then we can rewrite our rate equations here, substituting in the PA over RT and the PB over RT instead. And we're going to end up with setting these two equal to one another. Because at equilibrium, we already said the forward rate equals the reverse rate, okay? So we're going to set these two equal to one another at that point. Now, we talked about this in the last chapter. We can't just say that Kf is equal to Kr, right? We can't say that because if you think about your potential energy diagram here, remember, most of the time these things are endothermic or exothermic, right? And so the rate of the forward reaction here, in this particular graph that I drew, because this is an exothermic graph going in the forward direction, if I'm looking in the forward direction, this rate is actually faster than if I'm looking in the reverse direction, because in the reverse direction, your activation energy is all of this, because we're starting down here, okay? And so to get back on this reaction would actually take longer than to go forward in this particular scenario. So you cannot say that Kf is equal to Kr. Okay, but what we can say, so once we've rearranged this thing, is that the forward rate is equal to the reverse rate at equilibrium. And so then you can write it like this, okay? At equilibrium, the products are changing into reactants at the exact same speed that the reactants are changing into products. So we can write this whole expression here. Okay, hopefully that makes sense. I can clarify that in class if we need to. So rewriting this equation a little bit, if we rearrange it and then cancel some things, we end up with Kf over Kr equals Pb over Pa, okay? And this Kf over Kr right here, since those are two rate constants, when you divide two constants by one another, you get a constant, okay? And we're going to call that constant the equilibrium constant, all right? So what we end up with for, let's see, let me make sure. No, okay. So what we end up with here, if you have reaction A going to B, we end up with the equilibrium constant for this reaction. Once it reaches equilibrium, it's the pressure of B over the pressure of A. Okay? And so hopefully that makes sense. Now, the other way we could do this, this is written in terms of pressures. We could also do this in terms of concentrations, okay? So notice, if I don't do all the substitutions that I did before, if I just keep my rate laws as rate equals K forward times concentration of A, and I say that my reverse rate equals K reverse times the concentration of B, then I could do the exact same thing. I can say at equilibrium, the two rates are equal, okay? These are equal to one another. And so then I can say that Kf times concentration of A is equal to the Kr times the concentration of B. Probably should have shown you this one first. So then if you rearrange this one, you end up with, let's see, Kf over Kr is equal to the concentration of B over the concentration of A. Okay, and then again, this is just your equilibrium constant. So K EQ equals concentration of B over concentration of A. Right. Now, on our other derivation, we made one assumption that I should talk about, and the assumption here is that the temperatures stay the same. Okay, so because the temperatures stay the same, they're going to cancel out, and the only thing that's left is our initial pressure and our final pressure. This kind of comes back to what I was talking about when we did the gas law stuff, that if you have a constant volume, you have a constant temperature here, then you can use the stoichiometry ratio, or the mole ratio in the equation, to figure out the pressure ratio. Okay, so because those two things are essentially, mole ratio equals pressure ratio when we've got constant volume and constant temperature, we can do this this derivation here that relates these two things. Okay, where did I write? I guess I didn't write it. Okay, so then overall, we could also write here that the KEQ equals the pressure of B over the pressure of A. Okay, so either one of those works. All right, so the equilibrium constant, we're doing some experiments with it. I say we, scientists have done these experiments before, and this is one of the ways that they were able to figure out how the equilibrium constant changes based on the concentrations. Okay, and this is very closely related to the rate constant. Okay, so what scientists started to notice, if they graphed the concentration, or if they looked at the relationship between the concentration of NO2 and N2O4, there's not a real clear relationship there. Okay, if you take, in other words, if you take the ratio of the NO2 versus the N2O4, there's, this data right here, there's not a lot of consistency to it. Okay, but if you take the square of the NO2 concentration divided by N2O4, notice we get all these numbers that are exactly the same. Okay, and so what that's showing is, if we want to write our our equilibrium constant expression for this reaction, it would be NO2 squared over N2O4. Now notice something about the equation right here. There's a 2 in front of the NO2. Okay, turns out this 2 is related to this 2. All right, so I know I told you when we were talking about kinetics that you you need to determine these things experimentally. Okay, for the equilibrium constant, when you write the equilibrium constant expressions, you actually are going to look at the stoichiometry in the equation, because the coefficient tells you the exponent when you're writing your equilibrium expressions. Okay, and so you kind of have to, retrain yourself on this. And again, this is something that was sort of figured out experimentally. Okay, but you can figure it out mathematically as well. And just for the sake of time here, I'm not going to talk a lot about that at the moment. But this is called the law of mass action, okay, which we talked about those two scientists at the beginning who came up with this. But this is the general way that you would write your equilibrium expression, okay? We already talked about how it ends up being products over reactants. If you go back to the A to B example that we did, it ends up in both cases being products over reactants when you write the equilibrium constant expression. So we've got C times D over A times B, and then whatever coefficients are in front here, those are the powers that you raise your concentrations to. Okay? Okay, so at equilibrium, this K is always going to be the same. All right, just like we looked at in the example over here. If you take the ratio of these two things, which is essentially, that is the K expression, then you end up with the same number every time, okay? And that's your K. That's going to be the same no matter what, as long as you are at constant temperature, okay? Doesn't matter what your concentrations are, that K value is always going to be the same. So if you know your K value, and you know some of your concentrations, you can figure out the concentration of the other ones. Again, law of mass action, This is just restated here, okay? K is the equilibrium constant. It is unitless, all right, because you're going to end up canceling out your units here. Okay. The magnitude of the values. So this sort of tells you something, okay? If you've got a KEQ that's large, that means the numerator is larger than the denominator. So coming back over here, okay, if this K is a large number, then that means these numbers must be bigger than these numbers, okay? So if that's the case, what that's telling you is you have a higher concentration of products than you do reactants, okay? And so what that means is basically you've got a lot of the product and not a lot of the reactants in your equilibrium, okay? So the point at which the rate forward and backwards becomes the same is a point where you have a lot of the product and not very much of the reactants. Okay, so the opposite of that is if a KEQ value, this is supposed to be a capital K, I apologize. If the KEQ value is small, that means the denominator is larger, okay? So it's the opposite here. So that means that this number is big, this number is small, okay? So in other words, our equilibrium favors the reactants, which means there's going to be a lot more of the reactants present at equilibrium than the products, okay? So again, I just want to stress, equilibrium does not mean you have equal concentration of reactants and products. It just means that the rate of the forward and reverse reactions are the same. Okay, we just talked about this. Large values for K means the reaction is product favored. When equilibrium is achieved, most of the reactant has been converted into product. Okay, so at equilibrium, this is going to be your, your concentrations. Lots of product, not very much of the reactants. And then the same thing for, the other way. If you got small values for K, that means there's a lot more of the reactant and a lot less of the products. Okay. Writing an equilibrium expression. This is very easy stuff. Okay. Let me make sure that we're tracking on the notes here. I should be doing this more often. We talked about physical equilibrium. We talked about the equilibrium constant and how to derive that. Talked about the law of mass action, magnitude of the KEQ values. That's where we are right now. And I'm writing an equilibrium expression. Okay, so we're right on track here, which is good. Sorry, I'm trying to get through this as fast as I can. This is basic stuff, but there's just a lot of new material here. So if we're going to write the equilibrium expression for this reaction, then basically what we're going to end up with here, we need to put products over reactants, and we need to take into account the stoichiometry here. So NO is one of my products, and I need to square it because of the coefficient 2 in front of it, and multiply that by the O2. And actually, these are gases. It's not specifying here which way I need to write this. I guess I could write this two different ways. And we're going to talk about that in a minute, actually. Okay, so I could write it in terms of concentration. Or, these are all gases, so I actually could write this in terms of pressure as well. Okay, so that's one way that I could write the rate. So used to saying rate law. That's one way that I could write the equilibrium expression. Another way that I could write it is in terms of pressure. So I could say the pressure of the NO squared times the pressure of the O2 divided by the pressure of the NO2 squared. And maybe I should put that on the outside. Like that. Okay, so that's another way I could write the equilibrium expression, just depending. Whoops, there it is. Okay, it looks like I was thinking in terms of concentration on this one. But again, you can write it in terms of the pressure like we talked about before. Write the equilibrium expression for the following reactions. Okay, and again, this should be fairly easy. We'll just stay in terms of concentration on these for now. So the first one here, your K is going to equal O2 cubed divided by O3 squared. Okay? See how easy this is? It's not hard at all. B, I'm going to have to come down here to do K equals NOCl squared over NO squared times Cl2. And then our last one here, our K equals Ag NH3 2 plus, you should recognize what that is. That's a complex ion. Divided by Ag plus times NH3 squared. Okay? So there's all our equilibrium constants for these reactions. So again, just another example here, using the magnitude of the equilibrium constant. All right. So here's a reaction of N2 with O2 to form nitrogen monoxide. Okay. It's saying the value for the equilibrium constant for this reaction at 25 degrees Celsius. Again, this is important. If you change the temperature, you change the equilibrium constant. We're going to talk more about that later. But the equilibrium constant at normal room temperature is 1 times 10 to the negative 30th. Okay? That is an extremely small KEQ. So what that tells you is, at equilibrium, there's going to be a lot more of the reactants than there is of the products. Okay? In other words, not very much of this reaction changes into products. Okay? At equilibrium, you'll have just a tiny bit of this, of the NO, and a bunch of the N2 and the O2. Okay? So the feasibility of this reaction for nitrogen fixation, if you want to produce NO, this is not a good way to do it. Okay? At 25 degrees Celsius, this reaction is not going to happen very quickly. Now there are things we can do, like change the pressure, change the temperature, that can force the equilibrium more towards the product side. But as this reaction is written at 25 degrees, this is not a good way to produce nitrogen monoxide. Okay? Okay, what are we doing here? Let's see. The equilibrium expression for a reaction is the reciprocal for a reaction written in reverse. Okay, which kind of makes sense. If you write the reaction in reverse, then obviously you get the reciprocal of that. Okay? So, okay, we're talking about how you can manipulate K. All right? So, what it becomes is basically the inverse of K. All right? So if I have a reverse, or if I write the reaction in the opposite direction, if I flip the equation around, then I change my K to 1 over K. And what we're going to kind of do here is like a Hess's law type thing, where we can add these reactions together, and we have to manipulate K based on what we're doing to the equation. So if I'm adding equations together, and in the course of that I need to, sort of flip this thing so that it's written in the opposite direction, then I have to take the inverse of my K. It becomes 1 over K instead. Okay? If you multiply the balanced chemical equation by a factor of n, in other words, again, like a Hess's law type thing where we have to multiply an entire equation by 2, or something like that, which I think is actually what's going to be shown here. No, we halved it. We multiply it by 1/2, I guess, to stay consistent with the example here. Okay, then it becomes NO2 yields NO plus 1/2 O2. Okay, what you end up doing here, it ends up being K to the 1/2 power. Okay, so essentially this K, if we change this, okay, if we rewrite this expression, so then now we've got NO times O2 to the 1/2 times NO2, we have essentially reduced the power of everything in that expression by 1/2. So then our K becomes half, it becomes to the half power of what it was before. Okay, if we had multiplied this whole equation by 2 instead, and this would become NO to the 4th power. This would become O2 squared. And this would become NO2 to the 4th power. Okay, so in essence, then it would end up being K squared. Okay, so giving the following information, determine the value of the equilibrium constant for the following reaction. All right, so now we're basically doing a Hess's law type thing. Okay, notice we can manipulate these two equations up here so that we can get the equation down at the bottom. Now let me make sure I haven't gone too far here. I can't remember where these notes cut off. Magnitude of KEQ, manipulating KEQ. Okay, oh yeah, and then we talked about KP, KC. Yeah, this is a lot. Okay, so I'll try and get through this as fast as I can here. So we've got two equations here, and we want to add those two equations so that we end up with this one down here. Okay. So what you might notice right off the bat is the H2C2O4 is on the reactant side on this equation, and it's actually on the product side over here. Okay. Probably what we're going to need to do is flip the bottom equation. But then you also might notice that the top equation looks like we've got 2 HF down here and only 1 up here. So we probably need to multiply this one by 2. Okay? And so then we want to determine the value of the equilibrium constant for the following reaction here. Okay? And so what we're going to do is we are going to multiply the first one by 2, the whole equation. We end up with, I don't know if I'm going to have enough room for this, 2HF yields 2H plus 2F minus. Okay, and our new K for this is now going to be, get out my calculator, (6.8 times 10 to the negative 4th) squared, because we have to square our K now. That's going to give me 4.624 times 10 to the negative 7th. Okay? And then our second equilibrium constant, once we flip this equation, we're going to end up with C2O4 2 minus plus 2H plus, it's convenient, yields H2C2O4. Okay? Now our K for this one is going to be the inverse of this K, because we flipped the equation around. So we take 1 divided by 3.8 times 10 to the negative 6th. That ends up being 2.6 times 10 to the 5th. Okay? So then when we add these two together, then you're going to end up getting your overall equation here. Okay, it should match this one because, let's see, the H pluses cancel out, and then everything else looks pretty much like the equation that we have up there. When you add these two together, you're actually going to multiply these equilibrium constants by one another. Okay, so then once you do that, you get 4.624 times 10 to the negative 7th times 2.6 times 10 to the 5th. And you should end up with a new K at the end of this thing. I ran out of room down here. 0.120, if I'm doing that correctly. Okay? Alright, so now let's talk about Kc, Kp, and how they're related to the equilibrium constant. Okay? Keq is just the general symbol for an equilibrium constant we're talking about. If we're talking about Kc, that's specifically with respect to the concentration. Okay, and I referred to this a little while ago. And you write this expression using brackets. Okay, your example here is like the law of mass action thing that we showed earlier. Okay, that's specifically written in terms of concentration. Kp is the equilibrium constant with respect to partial pressures. And this is a mistake. I apologize for that. There should be a P there. Kp equals, and then it gives you the expression with respect to pressures instead. Okay, and then you use parentheses, and then your exponent goes outside the parentheses. All right. The way that you can relate Kc to Kp, if you have an equilibrium constant with respect to concentration, and they want one with respect to pressure, you have this equation on your equation sheet, and typically you're going to be asked this kind of question on the free response section, not on the multiple choice. So you would have this equation at your disposal. So probably no memorization necessary on this one. I've only seen this come up in a couple of instances anyway. But here it is. The Kp equals the Kc times RT. R is going to be the 0.08206 because we're dealing with pressures in atmospheres most likely here, times the delta N, which is just the number of moles of gaseous products minus the number of moles of gaseous reactants. Okay, so usually when we're talking about relating the Kc to a Kp, we've got a gas equation. Okay, and so here's an example of this. We've got this reaction, CO plus Cl2 yields CoCl2, and the Kc for that is 5.1 times 10 to the 9th at 330 Kelvin. We want to know what's the Kp for the reaction at this temperature. Okay, so again, I'm going to come back to this equation. Kp equals Kc times RT to the power of delta N. All right, we know what the Kc is. It's 5.1 times 10 to the 9th. So we're going to multiply that by RT, which, let's see, our R here is 0.08206. I'm gonna put this in, probably should put that in brackets, times our temperature, which is 330 Kelvin. It's already in Kelvin, which is good. And then we take that to the delta N power. Okay, and remember again, delta N is the moles of gaseous products minus the moles of gaseous reactants. Okay, oops, wrong way. So our gaseous products, we have, looks like 1 mole of gaseous products here, and we have 2 moles of gaseous reactants. So 1 minus 2, that gives us a negative 1 here. Okay, so then when we multiply all this together, be careful with your order of operations here. I would multiply this part together and take it to the negative first power first, and then multiply it by the 5.1 times 10 to the 9th. And then let's see here, I'm getting to my Kp. I'm not doing that right. Okay, sorry. I punched it in my calculator wrong. Times 330, that gives us 27. So then basically we're taking the inverse of that number. So 1 divided by our answer here. That's what the negative 1 power does. And then when we multiply that by 5.1 times 10 to the 9th, that's going to give me a Kp of 1.9 times 10 to the 8th power. Okay, so I mean they're decently closely related, but they're not going to be exactly the same, Kc and the Kp. It just depends on whether you're writing your equilibrium expression with respect to pressure or with respect to concentration. Okay, all right, so we are finally done with that one, and let me make sure again that we've covered everything that was on the notes. I don't want to miss anything here. Yeah, that was our last example. Okay, so we will talk in class about that on Tuesday, and we'll just go from there with the equilibrium constants. Have a good